Good morning and good afternoon. Welcome to ARA's Webinar Wednesday. I am Sri Rao, your moderator for today's webinar by ARA's NEA division. The title of today's presentation is How VISE, V-I-S-E, which stands for Virtual Integration and Simulation Environment, and MPMS, which stands for Mission Planning and Management System, work together to enhance mission success. Now I'd like to introduce our presenters, Jeff Hyams and Robert Belle-Isle. Jeff is the Mission Planning Group Leader at ARA's NEA Systems Division. He has been a Senior Robotics Software Engineer since 2012 and was recently promoted to Principal Robotics Engineer. Jeff has extensive expertise in mission planning, open standards, and architectures. He has been working in mobile robotics since attending grad school in the late 90s, where he earned his MS in computer science from University of South Florida while researching applications of marsupial robots for urban search and rescue. Jeff has extensive experience with JAUS and UCS standards. I don't know what they are, but Jeff is the expert on that and has served as an active member on both SAE AS4 working groups. Jeff served as the task group leader for the AS4UCS multi-domain extensions that extended the Office SAE UCS model with maritime and ground domains. He has also led efforts to demonstrate the viability of the Universal Tactical Controller Architecture, which is an open systems designed for creating a common controller for unmanned ground systems. Jeff has been a big part of the development of the Mission Planning and Management System, the MPMS system, for his entire career at ARA's NEA System Division, and has been the mission planning lead for the entire system for more than 7 years. So, Jeff, I'm really glad that you are able to present in today's webinar Wednesday. I'll also introduce Robert at the same time, and Jeff and Robert will take turns with the presentation. Robert Belle-Isle is a Senior Robotics Software Engineer and the Simulation Team Lead at ARA's NEA Systems Division. He joined ARA in 2021 and has been a core developer and is the architect of VISE, which is a digital platform for testing, training, and validating active AI systems such as off-road autonomy. During his time at ARA, Belle-Isle has worked on numerous efforts to integrate autonomy systems with vehicles in both real and simulated worlds. For project contributions, Mr. Belle-Isle on the DARPA Racer program, he's on the DARPA Racer program, and he developed a testing framework for high-speed off-road autonomous missions using a simulation platform that has been integrated with the ARL Phoenix Autonomy Stack. He also has developed the architecture required to train reinforcement learning-based autonomous systems using digital twins for same-day vehicle deployment in the real world. Currently, he's leading the development on the next generation update to VISE, and he's pushing ARA's high fidelity and real-time simulation capabilities into new frontiers by helping solidify ARA's NEA Systems Division as the top contender in the race to generating synthetic data for training artificial intelligence. Belle-Isle received a bachelor's in mechanical engineering from the University of South Maine in 2020 and earns his master's in engineering with a focus on robotics from Stevens Institute of Technology in 2021. So, Robert, I'm really glad you're able to present today as well, and thank you for presenting. Jeff, I'm going to turn it over to you. Thank you.
Thanks, Sri. I'm going to start here with just a little bit of a history of NEA Systems and the NEA Systems division of ARA. So we were founded as a small SBIR-based company in 2009 by Dr. Parag Batavia. We were acquired as a wholly owned subsidiary of ARA in 2017. And for the life of the company, we kind of have 4 main contribution areas, but we are a leader, if not the leader, in off-road unmanned ground autonomy systems with our N-Drive system. We do, and are a leader in multi-robot mission planning, which I'm going to talk about today. Obviously, as part of all of that, we have advanced simulation systems that Robert's going to mention and talk about. We've recently taken up a heading cybersecurity with trusted UGV programs with AUVSI. We have a very extensive perception and machine learning systems. And bringing that all together is we believe very, very strongly in open standards and open architectures. We have many people that serving, myself included, on robotic standards committees and boards, and leading a lot of the ground autonomy standards like JAWS and IOP. So what are we going to talk about today? So first, we're going to talk about VISE, Virtual Integration Simulation Environment. That's Robert's going to go through that with you about all of our simulation systems. And I'm going to present and talk about our mission planning and management system. We're going to wrap up just talking about how those systems work together, how they combine, why each one benefits each other, and then we'll end with just a wrap up and questions and discussion. So Robert, I'm going to hand it off to you for VISE.
Hey, thank you. Hello, everyone. Thank you all again for coming. My name is Robert Belisle, and I'll be starting us off with a discussion about our simulation VISE. Before we get into VISE and how it's used with MPMS, I did kind of want to give a brief overview on the actual type of simulation it even is, and provide context to everyone on what is kind of required from VISE for us to actually even integrate these very complex autonomy and mission control systems. So if you can move on to the next slide. The first question we will have is, why do we even need simulation? For our systems to be successful, our developers have to be able to test their code. Without a simulation, the only way they could actually do this is by running on physical hardware, something like the Polaris MRaiser that's shown in the picture here. You would load this up onto a trailer, bring it out with the team to some location, and then you would execute all of your missions there, and that would be how you would test your code. The reality of testing on real vehicles is that it is extremely time and cost intensive, though. Especially if something goes horribly wrong, the last thing you would want is for your engineers to have to spend hours getting everything all set up just to find some issue, and the entire process end up getting halted while they have to debug the issue out on the field. And for hardware-first focused groups, this ends up being a very common pain point. A core reason to have a simulation to test in is to kind of avoid this entirely. By ensuring code functionality prior to deployment, you end up saving a massive amount of time and money. And this is why at NEA, we test everything in simulation. So to be able to do that, we've kind of determined the critical components to a successful development environment for autonomous systems. And on this slide, we detail a few key points, and we're going to end up diving into those more on the following slides. These range from an online system that provides data streams from simulated sensors or whatever you need from it, to multiple vehicles that all kind of run in diverse environments. Moving on to the next slide, please. We can start to look into what our simulation provides. The biggest one that we've been talking about is that it does need to be a development tool. This needs to be something that's made for users. By providing users with a real-time simulation that gives them interfaces which are identical to the real vehicle, they can launch their code with the assurance that they will see the same behavior if they actually go out and do the same thing on a real vehicle. And a surprising amount of this is actually related to making the system itself easier to use. For example, the requirement that we have on this slide, the first one, is that the simulation and the autonomy both need to run on the same laptop. This is actually a really critical component to a good simulation. And very often, simulations like this can be extremely expensive resource-wise, and ends up making them very difficult to use. So for us, it's critical that any developer at any time could very quickly launch VISE alongside the systems that they need to test on their own personal development setup, somewhere that they're comfortable developing, and then have access to all the tools they would need to appropriately test it. Additionally, the ease of use for running missions is a big one too. We want VISE to be configurable so that you can either replicate missions that you would run in the real world, or construct missions from the ground up that may be able to test certain cases. And this brings us on to the next slide, where we're going to take a more in-depth look at the edge cases themselves. Since we are in a simulation, we have access to running tests that would either be unlikely or just plain dangerous to do in the real world. But it might still be something we would want to see our system respond to. And while the example here is relatively extreme, and it's not really one-to-one with an actual required test case that we do, I like to bring it up because I really think it highlights what we mean by testing edge cases in simulation. Here we have an MRaiser that is given orders to run an autonomous mission that would drive it off of a cliff. The path goes off the cliff. And we also specify that it needs to drive something like 30 miles per hour at that cliff. The goal would be that the autonomy sees the cliff and stops in time. So on the left, it stops in time. On the right, you don't stop and you know what happens. By performing tests like this, we can close a tremendous number of gaps that would have otherwise remained unknown. So when we talk about edge case testing, this is the kind of thing we're looking at. And additionally, due to the way that VISE works, we can configure pretty much any kind of test. And we're going to actually talk about this a lot more in detail later. But first, if you can move on to the next slide, the last thing I want to talk about that VISE provides, or the simulation provides, is that it can generate synthetic data for training and evaluating AI. And this is a very big thing now. Since we have full knowledge of the simulation's internal state, we can acquire the ground truth for anything, whether that be the odometry or position of a testing platform, or just getting out fully classified sensor outputs. Some of the pictures here show examples of us doing this with a depth camera on the left and its classified image right next to it, a LiDAR output of an off-road environment on the middle there, and then an IR sensor returning the heat signatures from an environment. Some of you might have even noticed that the first image, the one with the depth camera, is actually an environment that's provided by an open source tool. And that open source tool is called Carla. I will get into this a bit later, but a sneak peek on VISE's capabilities is that it is very open source friendly. And because of that, it has access to many different tools, which greatly expand the types of data it can generate. And with all of those types of data, in order to be able to generate the sheer amount of it needed to actually train systems, we have the ability to run faster than real time. And now this is either going to be locally based on a setup, or we can distribute the system across many GPUs and parallelize the process. Next slide, please. Now, I want to quickly look at just the kind of technical requirements of the simulation. And this is something that our group calls an autonomy integrated simulation, or AIs for short. The image here shows a rudimentary control loop between an autonomy system and a simulated vehicle. Here, the autonomy gets sensor feeds from the simulation, something like the depth camera that's on top of the car here, and it uses those to do some sort of internal logic. It constructs a world model, creates a cost map with it, and then generates maybe a plan through it. And with that plan, it then can construct vehicle controls, and these would be something like throttle and steer. These inputs go into the vehicle, or the simulated vehicle, and the simulation then processes the movement that would have happened due to that throttle or that steer change. Thus, this changes the sensor. This changes the sensors output, which then the autonomy sees it as a difference, and it kind of continues this. Over many time steps, the vehicle will end up moving around the simulated environment as the autonomy makes new decisions and sees new things. It's very much a digital twin of what you would see in the real world when you do this thing, when you do this on a physical vehicle. An important concept here is that these clocks are fully synchronized. The autonomy needs to be running at the same rate as the simulation to best align with what the real world would look like. If the autonomy starts running faster, or the simulation runs faster than the autonomy, you can kind of desync between the two. And this isn't something that happens in the real world because, we live in a continuous environment. Whereas with a simulation, you're always doing time steps. So that's a hypercritical component to an autonomy integrated simulation. Okay, and then on to the next slide. With all of that, we can kind of get onto VISE itself. So if we add together all of what we've talked about, we get the VISE purpose, which is on the first thing on the slide here, which is to provide an active real-time simulation for testing, training, and evaluating AI systems across all platforms and environments. And this whole statement, as mentioned, is loaded with all of the information that we just went over. Everything of what we just talked about, this is what that means. This simulation is very feature-rich, and it allows a user to configure every aspect of its world, from changing the weather to modifying obstacles in the environment, the sensors on the vehicle and where they are and their internal parameters, and even the terrain itself. We can modify that. All of this can be modified at runtime whenever we want. You don't need to turn the simulation and turn it back on to change things. You could do it while it's running. It is also something that we call autonomy ready, in that it's been optimized for integrating autonomous systems with, and that is something that we've already done across many different stacks, DoD, commercial, and open source, which is made possible by the many different communication channels that we have to accommodate this. As I mentioned earlier, we need to be able to create the same interface that a vehicle would provide, and predominantly in the space we're in, the robotic space. This is with ROS1 and ROS2, the robotic operating system. But we also support socket communications as well, which can be pretty common with sensors or lower level control on a lot of the ground vehicles that we work with. Additionally, due to the way that VISE is built, it's all very highly modular and extendable. So many more communication types could be integrated with it as is. And on the next slide, we show an array of different features we've created. Since VISE is built on the Unreal Engine, we have access to many open source tools, as mentioned before, Carla, but there are others as well that we have access to. Pretty much anything built in the Unreal Engine could be leveraged in VISE. Unreal is a modern gaming engine that gives us full control to use built-in physics that it gives us, or leverage our own custom physics to perform pretty much anything we want. Whether that be creating a LiDAR sensor that has accurate returns on vegetation. This would be the bottom left image where it says vegetation aware LiDAR model, or something like a caterpillar with an articulated bucket that can perform dig and dump cycles and fill, pick up some dirt, fill a hole. This would be the bottom right image as an example. By leveraging all of this modern gaming functionality, we can very rapidly generate new environments, vehicles, or features. In that workspace, we can also work with systems that are in any environment, land, air, sea, any type of, and with any type of function or mission. Now, if you can move on to my absolute favorite slide, we get to kind of the crowning feature of VISE, and this is RapidT, the rapidly produced and integrated digital para tool. This is a tool that allows us to create entire digital worlds from scratch, all at runtime and in seconds. We can generate the terrain and the features on that terrain. This includes vegetation, roads, buildings, so on. Pretty much everything you'd see when you actually go out and run tests. Then, after it generates it, we can immediately deploy autonomous vehicles, like the M-Razor we showed or any of the other vehicles we have, in that environment. So, with this tool, our users can deploy anytime, anywhere. And kind of a fun benefit to how we made this one is that it can also generate things that aren't real, which kind of sounds funny at first. But I want to take, for example, if I'm trying to set up an autonomy system, and I just want to test my autonomy in a pretty straightforward situation where it's maybe a mostly flat world, but it has some randomized rocks and maybe some randomized bushes. And I just want to make sure that if I run that tests over and over again, maybe across a Monte Carlo style testing setup, that it's always successful. I can always drive through that kind of pretty simple environment. The agnostic input data for this tool allows us to generate millions of seeded iterations of that test. And this brings us to the final slide on VISE today, the Simulation Management System, or SIMS. Now that we have the capability to generate millions of iterations of a test environment using RapidT, we also have a tool that's built to run those tests. SIMS is a queue management system in Web UI that lets users completely define their scenario, the number of tests, what's in the environment, the mission, everything, and then just hit go. It'll automatically leverage either cloud or local resources to start creating the containers with those systems, performing those tests, and as it does it, it'll generate metrics and it'll put those metrics on a UI. You can kind of see it in the top and the bottom image. You can kind of see some graphs and you see a list of different tests that were run. It can also be used to run simulations for generating the synthetic data and then using that for training the machine learning. As mentioned earlier, since VISE can generate that data, and we can also create millions of iterations of different testing environments, this tool can be used to generate that sheer mass of data at faster than real-time speeds. So this tool kind of brings together everything we've talked about to be able to train larger models. For us, SIMS closes the loop between development testing and full-on testing and evaluation for production-style products with VISE. Now, with that, I will pass it back over to Jeff to talk about MPMS and how it uses this simulation. Thank you, everyone.
Thanks, Robert. Jeff, thanks for that awesome overview of VISE. I'm going to talk about our mission planning and management system. And I'm going to jump right into a slide I like to present all the time on what is mission planning and how do we define that. And that's really important in robotics because the words mission planning are overloaded a lot into sometimes it's a single vehicle path planning, sometimes it's maybe some minor coordination. For our system, the MPMS system, is we look at it as the highest level of mission planning. So how can we do what a lot of people might term fleet management or coordination and tasking of large numbers of systems that are completely heterogeneous and disparate, might be manned, might be unmanned. And so what does MPMS actually provide? It coordinates existing behaviors within all of these systems to work together to perform missions and tasks. It's fully distributed and vehicle agnostic. I'll talk a little bit about the how everything's implemented in a few slides, but basically we are completely agnostic to the actual vehicle type when we're designing and running a task, and there's an integration an engineer does on a vehicle. We have high-level scheduling and asset assignment. If I have 50 assets and I have a mission and I want to know what the best assets to perform that mission are, I can select and it will suggest assets. And then lastly, and more common now, is if you're going to control multiple systems, there is a large aspect of user interface and cognitive load and cognitive science involved in what does it actually take and what data needs to be presented to be able to understand what's happening when you're looking at a map with 15 or 20 systems performing a mission. What does MPMS not provide? It's pretty critical here. It's not going to add an existing perception system to an individual robot. If it can't detect people before you integrate MPMS, it's not going to detect people after you can integrate MPMS. And it's not going to add or add a basic autonomy behavior. So if it's not an autonomous vehicle that can do autonomous path planning, MPMS is not going to add that. Now, I'll talk a little bit about later, it can take these individual simple behaviors and allow a user to combine them into a combined behavior. That's a higher level behavior that uses, for instance, people detection and autonomous path following to create a new behavior, and it can do that without a single line of code being written. So that's kind of what is MPMS. And now jumping into why MPMS and what's a little bit of the history of MPMS. So MPMS was actually NAA's very first Department of Defense SBIR in 2011, I believe. Since then, it's been funded by many different agencies, many different domains, over $19 million invested over about 15 years. We've integrated many, many systems from small ground robots, PackBots, Talons, all the way up to a full-size KMAX helicopter for CASEVAC missions. We've performed many, many operational field experiments. Early on, that was a lot of simulation, a lot of testing. But lately, we've performed missions with actual soldiers executing with MPMS to perform what we would consider real-world relevant missions. The last one was last year for the 10X event. Was a RAS platoon at Fort Benning, executing a 2.5-kilometer move to contact, followed by a hasty attack, hasty defense, and a consolidation and reorganization mission, controlling 9 different systems, 3 unmanned ground tracked vehicles, 3 quadrupeds, and 3 UAV drone vehicles. And that was all controlled and executed from a single controller, which the platoon leader had. And then lastly, I do really want to mention, we at NEA and ARA, we feel it's really important to be good stewards of the government's funding and money. This entire system is provided with government purpose rights. We feel that we want to get this in the field. We want to get it operational. It's going to provide a benefit. That's just our feelings for that, for licensing and purposes for that. I think it's really important. So now I'm going to jump right into the how. So how does MPMS actually function? What's the high-level architecture look like? How do we do what we're doing? So when we first started out, the real definition of mission planning was, how are we going to go from one-to-one control, or even many-to-one control, which is what we had in the 2011 range. You had PackBots, Talons, EOD robotics, where you have a controller. Even drones, class 2 and above, then you've got a huge command station, might be 4 or 5 people actually involved in controlling one single vehicle. So what is the question there from that point was, how do we go from that to a one-to-many, a true one-to-many control? So how can one person actually command and control many robots? And to do that, we first separated the concept of control and the concept of this high-level control into 4 main components. So on the top left, we have our mission planning tools. So we call this kind of this a priori mission planning. We realized early on, we want to let people who aren't software engineers be able to create new missions and tasks. That's a really important feature because you don't want to have to, if you have a new mission type come up, or you want to add and integrate a new mission type, you don't want to spend $500,000 to a software engineer. You just hand it to someone and say, hey, write a new mission for this and go test it out. So that's all done a priori, offline. And then the outputs of that gets loaded into what we call the operational missions. And that's separated into 3 pieces. So we have the operator user experience in the bottom right here. You see that? Right now, that's mostly integrated with the ATAC platform. We have an ATAC plugin, allows the user to create missions, assign missions, set features, draw search areas, things like that. But it's a distributed system. So we have previously integrated with a web UI, a Java UI, WMI from GVSC, various different interfaces. So it's not an interface that's required. We have a workflow, but that's that part. Then internally on the system, we have our mission management side. So this usually resides either on the tablet or somewhere on the control side, and that provides all of the mission management features. So we have a mission manager, which is a service that provides all of the interfaces and control to access the vehicles. We have the tasks, or the automated scheduling and automated task assignment services will exist there. We have template features. So if you want to draw a box and generate a search area, things like that. That's where all of those kinds of things reside. Path deconfliction algorithms might reside on there. So we have this kind of control segment piece that runs a bunch of distributed services that have all of these algorithms available. And then on the vehicle side, we have what we call mission executors. And what this does is it takes away from the requirement that our entire system internally, all the pieces have to match and meet a particular vehicle's protocol. We knew early on when we designed this system that we're not always going to have access to the vehicle's internal protocols. Some of them are proprietary. Some of them are open standards, and you can work with those. But what we wanted to show is that there's an easy way to integrate a mission executor, call them MEs, on a vehicle. And then once you do that, that vehicle is capable of performing any mission that's been designed in MPMS. So those are the 4 main pieces of MPMS and the high-level chunks. So then to jump down into the actual systems architecture and software architecture and what that looks like. So from left to right, you've got vehicles up to controller. So obviously I talked about the vehicles. You've got MEs representing a vehicle. They can represent a manned system, an unmanned system, any asset, any capability that executes in the real world. We've integrated with the SMET platforms, quadrupeds, drones. As far as the system's concerned, an asset is just something that can run behaviors. Then there's comms. Internally in MPMS, we have a messaging and a comms system and message types that are all defined as JSON schemas. It's obviously open. That's just the way we do things. But the actual protocol and transport layer is independent. We have a plug-in system. You can replace the comms with whatever you want. Because we know that we're not radio designers, and radios change, protocols change, transport changes, so it can be integrated with anything. And then when you go towards the right, you see you've got these services that reside and can be accessed through REST interfaces to any user interface. So we look at user interfaces mostly as presentation layers and not as executing algorithmic mission planning. So the views that you see in ATAC or Web UI or WMI or any of our presentation layers are actually just representations of the current state of the system, as well as allowing you to change that state. It's not, necessarily internally inside that ATAC UI plugin going to be executing or doing any kinds of mission planning algorithms. Those reside on services separately. The reason we do this and create this distributed nature is because a lot of these algorithms, a lot of these services we expect could possibly be reused and integrated with other architectures. So there's no necessary requirement that you use the full gamut of everything that MPMS provides just to do mission planning. There might be other systems that might just need the ME system or just need the UI or just need some of the services. One of the core unique things about MPMS is our mission planning tooling and how we do and look at planning. We call this Plan T or Plant. And what this tool provides is a graphical representation of a task that's going to be performed on a system. So the core concept behind MPMS here is that an individual asset is going to run a task. And that task is a loosely coupled thing with other tasks that are running at the same time. But on a single asset, an asset defines behaviors. And what we define as a behavior is just an abstract interface to something. So one of the behaviors we define, for instance, is called traverse to. And what that abstract interface is it takes in a list of waypoints. It has some configuration values of like what speed or altitude or whatever you want to fly or drive. And it outputs when that list of waypoints has been finished executing. That's the entire behavior. So when you integrate on a vehicle, MPMS doesn't care how that behavior is executed. It doesn't care if it's using NEA's N-Drive system on a ground vehicle or if it's using PX4 on an air vehicle. That behavior is just signal comes in with waypoint list, signal goes out with waypoint list has been executed successfully. Some of the other behaviors that we've implemented on here, if you look at this graph here, you've got at start, it executes a traverse to behavior, followed by 2 comms and battery monitor behaviors. And what those services do basically is say on startup, if my comms gets below a certain level threshold or my battery gets below a certain level threshold, fire a signal out of this behavior. So that's the interface. How it determines what battery level is up to the vehicle, right? We don't really care as far as mission planning goes, but we care when we do integration. And then if we go from left to right on the middle here, so once it's traversed to a known location, it's going to start executing a search behavior. And in this behavior, you give it a polygon, and it's going to execute a traversal within that polygon based on some sort of search algorithm. And that may be a lawnmower pattern, a zigzag pattern, or in the case of a drone, it might be what's your optimal path based on your camera frustrum and all your detection stuff. And at the same time, you can see here, there's a basic detect object service running. Whenever a target recognition or target is hit, it's going to send that signal with data on it into this orange box, which is a mission parameter. So when I said before that these tasks are loosely coupled between systems, that's how we do this. It's just like if you have a squad or 2 squads moving on a move to contact, and one of the squads makes contact, they might radio in contact at this location. That's what's happening here. It's saying, hey, anyone listening, here's information. And I can have another task that's listening for that same piece of data that could send another vehicle out to track that target or neutralize it if necessary. And then here, once you're done with the search, it's going to execute a traverse to back to home or to a known location that you want to go to, and then end. And then separately in this task, if one of these comms or battery monitor thresholds are hit, it's going to execute a traversal back to some known good comms location or back to home if the battery's low, for instance. So that's the mission planning side, and we've trained soldiers for that 10X operation to actually use that system and create the missions hands off by us for all of the missions that we executed for 10X. So then on the back end side, how do we actually integrate to vehicles? We have what we call mission executors, and these are the things that take in, let me go back one, the machine readable format of this and execute it and interpret it and execute all of those behaviors correctly. And so really what an ME is taking, it's taking those behavior interfaces and integrating them into the actual autonomous systems of that particular platform. So for instance, we have an ME for our MRaiser Alpha platform that you saw in the sim before. We have MEs for PX4 drones. We have MEs for simulated generic vehicles. A particular vehicle type will have a particular ME node. What we can do is we have an SDK that we can hand to third parties and say, you don't need to know anything about MPMS. You just need to use this SDK. Here's some defined behaviors, run the code generation, fill in here for when signal comes in, fill in here for when signal comes out. Okay, now your behavior is integrated. And I can now run any task that has those behaviors in it for your system. And we've actually done this with several third parties over the last few years. We've handed it off. We have no knowledge of those vehicle interfaces. They're not done by us. People were capable of creating other ME nodes that we actually have executed. Over the years, we've integrated with many, many vehicles. Obviously, this program's been going on probably almost as long as when quadrotors started. So early on, we integrated with the early quadrotor systems. You can see here on the bottom left. We've integrated with the Raven, several different tracked and ground platforms. And then the more interesting thing is for several operations, we've actually created MEs for people. And the difference here is that when you're operating a system controlling robots, a lot of times, especially in a tactical environment, which is really our target environment initially for the system, is you don't want to be heads down looking at a screen while people might be firing at you, right? You need to maintain situational awareness. You don't want to have somebody watching your back all the time. And so what we've actually done is create an ME where the behavior that's actually being executed is a query to the user. And so the user can actually be heads up, doing their normal missions and executing things. And when a system triggers a parameter or something happens, that ME can say, hey, I need you to come look at this now, or I need you to answer this question. And what we actually did for that was a CASEVAC mission with a medic executing a CASEVAC to a helicopter where they could start the mission, throw the tablet in their backpack, and have a smartwatch trigger them and ask questions based on the mission flow. And in this case, it was, hey, the ground vehicles moved to the location. When you've loaded the casualty on there, let me know. Click yes, and then the ground vehicle automatically takes off, and then the flow of the mission works there. And that's a unique thing for maintaining that situational awareness. Back to why. When we started this in 2011, there were not a lot of robots available. They're super expensive, and the chances of a squad, a platoon, even a company having even one robot was pretty slim. But we knew that was going to change, and that's obviously drastically changing now. And there is a distinct need for a single command and control of multiple heterogeneous platforms. And it can't be a fixed thing that costs a lot of money to do new integration. And so that's really what this is. We're going to be seeing more and more systems being implemented and integrated and deployed. And to control those systems together, we need an architecture that allows that. And that's the distributed nature of the architecture. The pieces can be used in other systems. We've integrated with various other architecture platforms, from Lockheed's RailSA to WMI and GVSC. It's designed for integration with deployed systems. It's completely system agnostic. We need to bring new systems in. It's super easy. And more importantly, reducing cost, right? GPR licensing, that's a big deal. But also the task editor, right, is worth putting into the hands of people that are actually experts in the missions that are being run, the ability to create those missions and design them. So instead of what the current paradigm or the paradigm might be is, I bring in a subject matter expert, they tell me what missions are, and as a software engineer, I create those missions in a system as runnable. Well, we're just saying, okay, a system is made up of behaviors. You can connect those behaviors in however you want, and you connect those systems together however you want using this system. And that reduces hugely development costs, but also time, right? If you can come up with a new way to do something that integrates behaviors and systems, you can try it out and run it. Which brings us right to, hey, how are we going to use MPMS and VISE together to benefit us? And what problems does this actually solve? It solves the problem I just said, is we want to be able to hand these systems to people to test, to verify. For MPMS, it's hugely time intensive to actually go test with real systems. Robert mentioned earlier how long it takes to test with a single system and a single platform. Now, it's not like if you add 1 or 2, you're multiplying the time by 2. It's exponentially more difficult. You need a larger area, you need more people. If you're flying, there are requirements for safety flying and safety. And you need network. It's large network, extensive radios, which are very expensive. But if you want to test a new mission, if you want to test a new type of mission, if you want to test a new integrated vehicle, you really need to test it somehow, right? We're all developers. And it needs to be done. And so what we created for MPMS initially, and what we have are some really basic simulations that aren't part of VISE that provide just interface testing. So if I want to test whether a system is going to be able to handle a behavior or whether a behavior makes sense, we can do that in a basic simulation. But it doesn't provide the fidelity and the kind of capabilities that are needed to do a true test. We need to be able to test real vehicles in real scenarios. And I've been doing this a long time. It is prohibitively expensive to do that with real robots. The robots themselves can cost just physically, acquiring them millions of dollars. If you're talking about 5, 10, 15 robots. And then just the logistics and management of actually executing a single test with 10 or 15 robots is just prohibitively expensive and time consuming. For several of these events that we've done with real robots, we did a lot of simulation early on, and that helps. And then you get in the real world, and sometimes you get 1, 2, maybe 3 runs of testing a day. That's obviously not enough. And more importantly, it exponentially increases the time every vehicle you add. It is very, very, very expensive. And lastly, this falls into rapid T and just generally is I can go test in a single location, but that doesn't tell me a lot, right? We've done a lot of testing at Fort Benning at the Mount site there, McKenna, but that's not the same as testing in the desert or testing in various different locations without paths and buildings. So what did we do? How do we do that? Well, MPMS is the top end. It's controlling and managing all these vehicles at the top end, and it doesn't know that we're running VISE on the back end. Because as Robert said, if you're running a sim, you don't want to have special setup and special integration. So VISE actually does allow us to create and set up environments with 5, 10 vehicles and run missions, and MPMS doesn't care that it's VISE or even know. Right? In between, we could run the end-drive autonomy, or we could run just basic whatever comes with ROS now. And it's allowed us to actually do a lot of different unique testing, even for some potential commercial applications like mining or digging. Lastly, when we train with soldiers or we train with users, obviously, you don't want to do training with real systems. Once again, super expensive. Also very uncomfortable to be outside in the heat potentially. But you can execute and train users how to create missions, how to run missions, how to execute the system before you get out in the field and you're spending $100,000 a day. They can refine tactics. They can rapidly change integration with AI. And they can do this with VISE and MPMS without engineers sitting behind them, right? These are tools, you take them, they're running, and you just start using them. So just to sum up everything we just talked about, So very important here, the integration between VISE and MPMS is a big deal for us, but it's also just a big deal in general, is it's the whole entire system. You can plug in autonomy and stuff in the middle, but VISE gives you all of the capabilities to run lots of different emissions, lots of different locations, and MPMS is the top end. It's saying I can actually control and command and understand what's happening between 10, 15, 20, 30, 40, 100 systems. Government purpose rights, VISE and MPMS are both government purpose rights. Like I said, this supports our goal of making these systems deployed, being used, saving lives, helping execute missions, and allowing the government to use them without vendor lock, right? You know, we update them, we manage them. It doesn't change commercial licensing, obviously, but we feel as good stewards of the government's money that this is actually the correct way to go. Some of the next steps for VISE are multi-domain, so land, air, sea, cohesive simulation. So the MPMS side of that provides the ability to test the VISE side as well. So as we develop and expand VISE, we can use MPMS to say, all right, we can actually execute these missions. And then leveraging for commercial applications. So agriculture, construction, mining, you see a lot more robots happening, but I will say a lot of those are still in this phase of it's a closed platform, there's one-to-one control, it's executing this one thing, and then you wait, and some person is kind of constantly managing. The goal of MPMS is to get away from that constant control loop into a more of a command loop, where you're commanding a system to do something. When it needs your attention, it tells you. You're commanding other systems to do things, and they talk to each other and execute things. And then just generally, I just will plug NEA and ARA both. We look at things to how can we fit things together. We at NEA Systems Divisions, actually the MPMS team now is expanding within ARA. We have other ARA divisions and people working and helping with that. And we feel that just the general collaboration of all of these tools, but also all of the people within both ARA and NEA Systems Division is important. Thank you.
Well, Jeff, Robert, thank you very much. That was really, really interesting presentation. And I appreciate you guys presenting this on Webinar Wednesday. For participants on the webinar, you may now begin submitting your questions in the chat box. And Jeff and Robert will answer as many questions as possible in the time remaining. We hope you enjoyed today's presentation and that you will join ARA for future webinars. And we have many more exciting topics in the works. So please watch your email for updates or visit the Webinar Wednesday webpage. That's www.ara.com/webinars. And we do have a few questions come through, and I'm just going to let you guys decide who's going to answer these questions. So one of the questions had to do with how you got the information. So Rob wants to know, what is the underlying real-world data source for RapidT? Is it OpenStreetMaps? Does it have elevation data? So if you can talk about that a little bit, probably Robert, I guess.
Yep, that one would be me. Yeah, so really quick, I just want to talk about what can go into RapidT and where it could come from first, and then I'll talk about what the actual real-world data source that we use for one of the features is. So RapidT was made to be agnostic so that its input could really come from anything, and you could construct worlds from anything. So this could be from leveraging open source GIS data to you've taken LiDAR data from a vehicle and used that to construct the data to create the RapidT maps. We wanted to make it so that no matter what you used, you could make a world with it as long as it had the information needed to do it. But we also wanted to provide users with a really simple feature, because some people aren't going to want to try to figure out how to use LiDAR data to convert to that formatting and do all of that. So we created a tool where you could put in the latitude and the longitude, and it'll pull down, and it's very specifically Mapbox data, the GIS data, as well as a lot of the information about the objects. It'll pull that from Mapbox, and that'll be the tool, or that'll be the source that it uses when you use specifically the kind of built-in latitude longitude spawner. Now, Mapbox does have problems. Again, it's an open source data format. It's open source data, so it does have some discrepancies, and you'll find some issues with it. But you could also completely replace Mapbox with, there are a lot of proprietary ones that we use. We even have one internally at ARA called Edge 3D that can produce very high quality versions of what Mapbox provides. And when you generate worlds with that, you get a much higher fidelity world. So the higher the fidelity of the data you use to generate the world, the higher fidelity that RapidT will make. Thank you.
Thank you, Robert. I think there's a follow-on question to that from someone else. Joe wants to know, and I'm guessing this is also for you, Robert. So how does the system ensure the accuracy and reliability of the simulated outcomes when transitioning to real-world execution?
Yeah, so this is going to be predominantly whether or not the data that is being generated, so let's take, for example, a sensor, is going to be one-to-one with the data format that would come out of that sensor in the real world. So if you have kind of a sensor format, in ROS, they have a lot of generic ones for LiDARs, cameras, everything. You want VISE to output on the same communication channel that exact data format. And then when your system takes that in, it won't know if it came from the real vehicle or not, because it's receiving what looks to be the same thing. And then what's inside of that data, the accuracy of the world and the sensor itself in the simulation plays a huge role in sim to real transfer as well. So there are definitely always going to be gaps between simulation and the real world. But when you know what those gaps are, it's much easier to have a successful transfer.
Thank you, Robert. The next question is from Jason, and I believe this is probably for Jeff. So how does MPMS communicate with VISE to ensure real-time synchronization during mission rehearsal, I guess?
So yeah, in this case, we actually don't need to do that because the layer in between MPMS and VISE is handling the, quote, autonomy synchronization. So if, for instance, we're running the MRazor in VISE and the NDrive, NEA's NDrive autonomy system, those have time synchronization. MPMS doesn't need the time synchronization because it doesn't care. It's representative of the real. Now, if we're going to move into Monte Carlo style simulations where we can run faster than real time, then we will have to do that. But currently we use it as a real time, execution simulation system a lot for an actual user running. But if and when we move into integrating it with our Sims Monte Carlo system, then we would have to synchronize somehow and figure out how to speed up the time correctly.
Thank you, Jeff. And I'm curious, so what kind of training or expertise is required to use these two systems together?
I'll take that. That's a good. So both systems are, moving more towards production, higher TRL and deployment, and those include training manuals and training systems. For the MPMS side, I have done several one-day training scenarios and classes with users, and then handed off the system for use. There's a, obviously setup. I run everything on one laptop. That's kind of, Robert mentioned that earlier. From a developer standpoint, one of our general caveats is if we can run everything on one laptop, then we can do development, seamlessly and easily on our own. But Robert, I'll let Robert kind of talk about VISE in general, but I'd say from an MPMS standpoint, just getting up to speed, learning how to make missions, learning how to run missions is a relatively straightforward, 1 day, maybe 2 day exercise with actual scenarios and testing.
Yeah, and for VISE, actually, VISE was always developed to be user-focused. A fun kind of tidbit about it is that because we're an autonomy company, a company developing autonomy, we are, for the VISE, we are our own users. So even though we produce a product, VISE, which is a simulation for pretty much anybody to be able to use and run with autonomy, mission planning, what have you, we are our own users. So it's very important that we can use our own tool. And we make a habit of making sure that everybody at NEA is able to use it successfully using predominantly just the documentation about the product. And if that's true, then it's also true for others who would use it. And we've seen a lot of success going about it that way. To use VISE, it's entirely through text-based readable scenarios, scenario formatting, which is what you use to configure VISE in its real world. So there's no sort of like underlying technical expertise that you need. You just need to be able to write the scenario file that you want.
Oh, and I will also point out that all of our deployment currently, especially for developers, but in general, is a virtualization through Docker. So actually deploying both MPMS and or VISE is, as Robert said, is following the onboarding, following the deployment instructions. And we've had non-technical users be able to do both.
That's really great. Hey, we're almost out of time. There's one more question. This one is from Kate. How would the mission planning system handle a fleet with mixed assets that can execute the same behaviors but run different proprietary software?
So yeah, good question. And that is basically what the mission executor handles, is when you're executing something within the whole MPMS framework, it doesn't know that behavior is executing on a different vehicle. Those tasks are always the same. They're always based on a defined set of behaviors. And then the mission executor, a software engineer, actually takes that mission executor combined with the behaviors they want to integrate on their platform and integrates the actual software to talk to those autonomous systems. So if it's a drone, it might be PX4 or ArduPilot for basic autonomy and waypoint following. If it's NDrive or a ground vehicle, it might be NDrive. It could be Forterra's or somebody else's autonomy system. So from a standpoint of the mission, the system doesn't care. It just cares that those behaviors execute. Now, I think the real question gets down to, are those behaviors technically possibly going to execute differently? Yes. Obviously a drone's going to fly through the air. It's going to get through woods easily. A ground vehicle might execute a different set of ODOA. It might go right, it might go left based on that. But when we talk about MPMS, we're talking about a higher fidelity of command and control. So we really want to say, go to this location, go to these points. And how you get there is less important. I know it's obviously important, but you might have to tune your points correctly if you wanted to go left around something instead of right. But yeah, that's how that abstraction works. And we don't really even think about, when we're running a system, which autonomy is running or which platform or which AITR, for instance, is running. We just care that when it's running, it's generating, I found an object at this location, it's a car, the end.
Well, Jeff, thank you for the answer. We're out of time, so we'll just wrap the webinar up. If we did not get to your questions, presenters have agreed to answer questions for the next 24 hours. And we just ask that you make sure that your questions are not of a consulting nature and that you understand due to the sensitivity of the topic, responses may be limited. Next slide, please. On behalf of ARA, again, I thank you everybody for joining us today. Today's presentation is being recorded and a link will be made available on the ARA's Webinar Wednesday website sometime next week. And we will also send a PDA certificate to all participants as verified by our attendance report as being present for the full hour of the webinar. A copy of today's presentation will also be included, and just please allow us a few weeks, maybe about 3 weeks or so, to receive your certificate. Next slide, please. If you look at the presentations that Jeff and Robert did, you'll realize that we do a lot of cutting-edge, interesting stuff, and so ARA is a great company to work for if some of these topics are of interest to you. We are a 100% employee-owned company. We continue to grow dynamically and are always looking for great people to join our team. So if you're interested, please send a brief resume and contact information to www.joinara@ara.com. And thank you all for joining us today, and watch your email for our fall webinar schedule. Have a great rest of the afternoon.